In this web clip, we will explore the alignment methods available in the Cresset environment. There are two types of molecules in the Cresset software: reference molecules and comparison or database molecules. The reference molecule is in a preferred conformation or bioactive pose and can come from a variety of sources, including protein-ligand crystal structure, pharmacophore hypotheses, or multiple pre-aligned single conformations. The reference molecule is treated as a single fixed conformation and has the three-dimensional field point pattern that is preferred for activity. The comparison or database molecules are compared to the reference molecule. In order to do the three-dimensional comparison in a sensible way, the database molecules must first be conformationally populated, then each conformation for each molecule is aligned to the reference and a score is generated. An alignment score or similarity score of 1 indicates a completely perfect alignment, whereas an alignment score of 0 indicates a completely imperfect alignment. Two alignment protocols are available in the Cresset environment, each with their own benefits and liabilities. First, there is our standard field-based alignment, in which we use a combination of electrostatics, shape, and hydrophobic field points to align molecules and calculate a score using a combination of these feature alignments. This approach is independent of chemical structure and works well for libraries where there is a large degree of structural diversity. Looking at the results from the field-based alignment, we see that the alignment is in tune with what we would expect from docking results or X-ray data, in that groups that don't necessarily overlap perfectly. Examining bioactive poses of different ligands in protein-ligand crystal structures, we find it to be quite rare that substantial portions of ligand structures are perfectly overlaid or atoms found in exactly the same places. While the field-based alignment may provide a more sensible alignment of features in the context of what the protein receptor sees, the maximum common substructure method produces an alignment where common structure is overlaid so that non-common features can be quickly isolated and examined, very much a ligand-centric approach. This can be useful for identifying structure-activity relationships for a library built on a single scaffold with functional variations around the core. For more diverse sets, the maximum common substructure option is not preferred. Let's explore how the alignment algorithms work. In field-based alignment, the three-dimensional array of field points are used to generate and score the alignment. In scoring the alignment, we use a combination of field and shape-based similarities. We see from the molecules here that we have a reasonable field score of 0.66. Looking at the shape similarity, we have a score of 0.98. Using these two similarity features in combination, we get a combined score of 0.82. By default, we use 50% fields and 50% shape when we do our scoring. However, this option is customizable to the user preferences. As you can imagine, a three-dimensional field-based alignment can allow the comparison of structurally diverse molecules and reduce library reliance on a common scaffold. In essence, we are comparing molecules in the true sense of bioisosterism. We see in the picture that three structurally very different molecules have very similar field point patterns in their bioactive conformations. On the other hand, if we are working with a concentric series and wish to have a specific common moiety forced together in the alignment, we can use the maximum common substructure option. When the MCS option is turned on, a special conformation hunt is done. The common substructure with the reference molecule is held in the same conformation as the reference molecule, and groups that are not part of the common substructure are conformationally hunted. The resulting conformations are then scored against the reference molecule using the current scoring metric, with the top scoring conformations being presented as the top scoring alignments. Within the panel, we can also control how the routine handles hybridization and element differences. With normal, there is strict matching of the substructure. With permissive, the method ignores the element but matches on atom hybridization. For example, cyclohexane would match morpholine but not benzene. With very permissive, ring atoms can match non-ring atoms. For example, butane can match part of cyclohexane. To examine how an alignment is affected by the MCS options, we will look at a small set of PERK inhibitors that were published in 2012, and these have a common indolene core. The peripheral groups have some variation, but also much commonality in their structures. Let's open this dataset in Torch. In this file, we have the set of structures aligned to the ligand from 4G31 in our usual Cresset alignment method using 50% fields and 50% shape. If we look at the indolene core, we see that there is some variation in the positions of the atoms in the core and quite a bit of variation in the peripheral groups. Let's realign using the maximum common substructure. To redo the alignment, we will click the Align button, which launches the Torch processing dialog. In this panel, we tell Torch to do a normal conformation hunt and that the alignment protocol will be Substructure. To further control the process, click the Show Options button. In the Alignment tab, let's delete existing alignments and ensure that the MCS option is turned on. Press Start to begin the calculation. Now that the MCS alignment is finished, we see that the alignment of the indolene core is much tighter, along with much of the peripheral groups due to their common structural features. While the field-based alignment may provide a more sensible alignment of features in the context of the whole molecule, and indeed resembles the variations in alignment motifs that we would see in X-ray structure poses, the MCS results produce an alignment where common substructure is overlaid so that non-common features can be quickly isolated and examined. This can be useful for identifying SAR for a library built on a single scaffold, with functional variations around the core. For more diverse sets, the maximum common substructure option is not preferred. If you have any questions or would like additional information regarding the Cresset alignment algorithms, please feel free to contact us by emailing support@cresset-group.com.